Okay, for the first part of the calculus exam review, we are going to be looking at limits. So let's do just kind of a brief review of limits, or more importantly, when a limit does not exist, before we actually get started working some problems. So there were three situations in which a limit does not exist, if you go back and look at your notes. The first one that we're going to talk about is when the y values don't match as you approach from the left and from the right. So if you're looking at a graph, your y values are different as you approach a given x value from the left and from the right. And so that can look like a couple of different things, but our most common thing that looks like is our piecewise function. So let's say that I'm approaching an x value of 1 right here, and my piecewise function maybe looks something like this. Okay, so as I approach 1 from the left, my y value is right here, and as I approach 1 from the right, my y value is right there. So I've got two different y values, therefore the limit does not exist. All right, the second situation where a limit does not exist is when you're talking about an asymptote, or what you might call unbounded behavior. And so let me draw a vertical asymptote on here. Go ahead and have a horizontal as well. The vertical is really more what we're worried about since we're talking about our y values. And so even if they're both going up into infinity like this from the left and from the right, let's say as we're approaching the x value of 0 here, even though they're both going to infinity, that's considered where our limit does not exist. A limit as a whole can never be infinity. From the left and from the right it can be, but as a whole it cannot be infinity. And our final situation is our oscillating behavior. And a lot of times that'll deal with a trig function, and that looks a little bit of something like this. And so sometimes in just a few minutes actually we'll work some, looks a little bit like that. Where it just is going really, really fast up and down as we're approaching 0 right there. You'll see in just a minute we'll work some where there's nothing really that we can do to a problem algebraically to get it to where we could solve the limit, and therefore that's probably our oscillating behavior. Okay, so let's go to our review worksheet, and on number 1 we're trying to find the limit as x is approaching -3 of x squared minus 2x minus 15 over x squared plus 4x plus 3. Okay, so the first problem that I see is that if I use direct substitution, which is what I would like to use for a limit, where we just plug -3 in for all of our x values, down here on the bottom I would end up with 0 in the denominator. I can't have 0 in the denominator, therefore I'm going to have to do a little bit of work before I start to find the limit as x is approaching -3. Alright, so part of the work that I can do is to factor. That's one of my tricks that I can use to help me. So in this case, I'm going to factor the top and the bottom, and I'm going to hope that one of my factors is going to cancel out. So the top I'm going to have x and x, and my factors of 15 that will subtract to give me -2 is going to be 5 and 3, and I'm going to need for the 5 to be negative and the 3 to be positive. On the bottom, my factors of 3 that will add to give me +4 are going to be +3 and +1. And so there's my factors right there that's going to cancel out. Therefore, when I plug in my -3, I won't have 0 in the denominator anymore. So let's go ahead and rewrite like this. Remember to continue writing your limit before you set these things to be equal. Now I can use direct substitution, because now when I plug -3 into the denominator, it does not give me a 0 in that denominator. So I'm going to have -3 minus 5 over -3 plus 1, and that's going to give me -8 over -2, which gives me 4. So the limit as x is approaching -3 of this function right here is going to be equal to 4. Okay, on number 2, we're starting to work with a square root here. A lot of times when you're working with a square root, you can use a trick called rationalizing the numerator. And to do that, we're going to use a conjugate. That's where that word conjugate just came from. Okay, so first let's check on our direct substitution. And again, if I use direct substitution right here, that would give me 0 in the denominator. I can't do that. So I'm going to use my trick with my square root that's called rationalizing my numerator. So I'm going to find the conjugate of the top. And the conjugate is always the first term and the second term, and change the sign that's in between. First term, second term, and change the sign that's in between. And if I multiply by that on the top, I need to multiply by the same thing on the bottom. Okay, so when I go to multiply these things together, I'm going to go ahead and keep my denominator in factored form. Let's rewrite our limits so we can keep these things equal. So when I multiply the square root of x plus 2 times the square root of x plus 2, I get x plus 2. Then my outside and my inside will cancel out because that's going to be positive 3 square roots of x plus 2 and negative 3 square roots of x plus 2. And then my last will give me minus 9. I'm going to keep my bottom piece in factored form like this. And the reason why I'm doing that is because hopefully something's going to cancel out here in just a minute. Alright, rewriting my limit. Let's simplify that numerator just a little bit. So I'm going to have that be x minus 7 now. And then on the bottom I have x minus 7 as well. And there it is right there. That's going to cancel out. And at that point I'll be able to use direct substitution. Those cancel out. I still have the limit right now. I haven't substituted in yet. So that's going to leave me with a 1 on the top and the square root of x plus 2 plus 3 on the bottom. Now I can substitute in. So that will give me the square root of 7 plus 2 plus 3. So the square root of 7 plus 2 is going to be 3. That's going to give me 9, and the square root of 9 gives me 3 plus 3 gives me 1/6. Okay, on number 3, we're working with a piecewise function. So I'm going to find the limit as x is approaching 3. Of this piecewise function. All of that when x is not equal to 3, which is good because I'd have a 0 in my denominator if x was equal to 3. And then this right here is just giving me a point 3,4. So I can graph that very easily. I'm going to solve this piecewise function by graphing. Piecewise functions are usually very easy to do with graphing. So let's see if we can graph this right here. All right, let me start with just this piece right here. I'm going to call this y equals just for a minute. So I go over here and work with it just a little bit. Okay, I notice just by looking at that it looks like I'm going to be able to factor this thing, and I am up here on the top. And what's nice about that is that that's going to let these two things cancel out. So if you think back to pre-cal, when you graphed something like this, if something canceled out right here, that was going to leave a hole in your graph, and it'll leave a hole in your graph where it made your denominator equal to 0. In this case, I'm going to have a hole where x is equal to 3. And so if x is equal to 3, then y is equal to 5. So I'm going to have a hole at the point 3,5. Let's go over here and graph that. So there's my hole right there. And then I'm going to graph just this line is all that I have left. So I've got a slope of 1, or you could say you have a y-intercept of 2, either way. And so this is kind of what my graph looks like. And I'm only working with this graph where x is not equal to 3. So this is going to be everywhere except for where my hole is right there. Now where that hole is, it's now told me that I have this point right here at 3,4. So there's the point right there. Okay, but remember that a limit is not really a value. It's more of the idea of what y value are you approaching. And so in this case, my y values are approaching, going closer and closer and closer to 5 from the left. They're going closer and closer and closer to 5 from the right. And so the limit of this thing, the limit as x is approaching 3 of f of x, my function there, is going to be 5. So really, that point has no effect on the limit. Now if I was looking for the value, the y value, when x is equal to 3, then I would say that that is 4. But my limit is the idea of where is it getting closer and closer to as you're approaching from the left and from the right. Okay, number 4. We're looking at the limit as x is approaching 0. 1 over 5 plus x, which I'm actually going to talk about more as x plus 5, same thing. All right, let's start by checking direct substitution. I would be okay in this fraction right here, but when I plug in 0, I would have a denominator in the total fraction, so I can't use direct substitution. What I'm going to do with this one is I'm going to try to simplify this complex fraction that we have right here. So on the top, I'm subtracting these fractions. Let's find a common denominator. I'm going to use SMILE to do that. Feel free to just find a common denominator if you want, but SMILE tells me to multiply those. Keep the sign the same, multiply those. I'm going to use some parentheses, and again x plus 5 and 5 plus x are the same, and then SMILE on the bottom. So multiply those together gives me my common denominator over x. Okay, let's do a little bit of simplifying up there on the top. So that's going to be 5 minus x minus 5. And I'm just going to leave this in factored form. So hopefully I'm going to substitute into that in just a minute. And now my 5's will cancel out. So I'm going to do two things at one time here. I'm going to go ahead and write this fraction the way that it is. And I'm also going to multiply by the reciprocal, or keep it, change it, flip it. So I'm going to keep it, change it, and flip it. And now my x's can cancel out. That's really what we needed to happen so that I can use direct substitution at the end here. Alright, so on the top all I have left is -1, and on the bottom I'm just left with this 5 times x plus 5, which again you multiply out if you want to. Alright, now I can use direct substitution, so that's going to equal -1 over 5 times 0 plus 5, which gives me -1 over 25. Okay, on numbers 5 and 6, we get into some trig functions that I really don't have any way of working with. So on number 5, I'm going to have the limit as x is approaching 0 of the sine of x over 3x squared plus 4x. The only thing that I could do to this is take out a common factor of x in the denominator. Direct substitution is going to give me 0, but watch when I do this that there's really nothing that's going to cancel out with this. If you had a calculator, you could plug it in and you would see in your calculator that it's just probably going to be that oscillating behavior or something with some kind of vertical asymptote. Okay, so if I look at this thing right here, I can't take the x off of the sine. Those things are held together since this one is an angle. And so there's really nothing that I can do with this one. I can't rationalize the numerator. I can't put together a complex fraction. There's nothing else that I can factor. Those are really all of my tricks. And so I'm going to say that this limit does not exist. So if there's nothing algebraic that you can do to help it out, then it probably is a limit that does not exist. Same thing's going to happen with this one, except that on number 6, except I can't even take out a common factor of x on this one. If I was going to take out the x here with the x here, I would also need to be able to take out an x over here. And again, I can't. The sine and this x are held together. This one is an angle. There's nothing that I can do to that problem, and so this is going to be another example of a limit that does not exist. Okay, and our last question on this section about limits shows us the definition of a derivative. Let me write down our formula for the definition of the derivative, and they're using h. In class, sometimes we used h and sometimes we used delta x. But our formula for the definition of a derivative is this. It's the limit as h, or as delta x, is approaching 0 of our difference quotient. Looks like that. And all of that right there is equal to f prime at x. Okay, so on number 7, if I'm looking at the limit as h is approaching 0 of the tangent of pi over 4 plus h minus the tangent of pi over 4, what I want to do is I want to pull out of this the function and the x value that I'm working with. Okay, so if you look at your function, this function is on the outside of my x,